The James Webb Space Telescope is upsetting the apple cart. All of a sudden we realize that we may have to rewrite all the textbooks about the beginning of the universe in their quest to understand the first stars and galaxies that lit up the cosmos. Astronomers are still in the dark, but getting closer to enlightenment, one discovery at a time. That's the incredible, inescapable conclusion from unprecedented discoveries by the James Webb Space Telescope, or JWST, the 10 billion time machine that just officially closed its first year of observations designed to glimpse the faint infrared glow of the universe's earliest luminous objects. Webb's vision reached back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built, but its haul of galactic baby pictures has proved more bountiful than most researchers dared to dream. Simply put, candidate galaxies in the early universe are popping up in numbers that defy predictions, with dozens found so far, and that makes scientists free out. As Charlotte Mason, an astrophysicist at the University of Copenhagen, said, "We really weren't expecting this." In the weeks and months following JWST findings of surprisingly mature early galaxies, theorists and observers scrambled to explain them. Could the bevy of anomalous big and bright early galaxies be illusory, perhaps because of flaws in the analysis of the telescope's initial observations? If genuine, could they somehow be explained by standard cosmological models, or just maybe were they the first hints that the universe is more strange and complex than even our boldest theories had ever supposed? And the Big Bang Theory, was it wrong? Join us today as we dig deep into how the James Webb Space Telescope broke the universe. Let's get to the point to understand the dilemma. Let's go back to when the universe was believed to have been formed. After the Big Bang, the infant universe began cooling off. Within a few million years, the roiling plasma that filled space settled down, and electrons, protons, and neutrons combined into atoms, mostly neutral hydra. Things were quiet and dark for a period of uncertain duration, known as the cosmic dark ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see, called dark matter. It has exerted a powerful influence over the cosmos, especially at first in the standard picture. Cold dark matter, a term that means invisible or slow-moving particles, was flung about the cosmos indiscriminately. In some areas its distribution was denser, and in these regions it began collapsing into clumps. Visible matter, meaning atoms, clustered around the clumps of dark matter. As the atoms cooled off as well, they eventually condensed, and the first stars were born. These new sources of radiation recharged the neutral hydrogen that filled the universe during the so-called epoch of reionization through gravity. Larger and more complex structures grew, building a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The universe is expanding rapidly. The astronomer Edwin Hubble figured out in the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Think of the universe as a loaf of raisin bread. It starts as a mixture of flour and water, yeast and raisins. When you combine these ingredients, the yeast begins respiring and the loaf begins to rise. The raisins within it stand in for galaxies stretch further apart from one another. As the loaf expands, the Hubble telescope saw that the loaf is rising even faster. The raisins are flying apart at a rate that defies their gravitational attraction. This acceleration appears to be driven by the repulsive energy of space itself, so-called dark energy, which is represented by the Greek letter lambda. Plug values for cold dark matter and regular matter and radiation into the equations of Albert Einstein's general theory of relativity, and you get a model of how the universe evolves. This lambda cold dark matter, or lambda CDM model, matches almost all observations of the cosmos. One way to test this picture is by looking at the very distant galaxies, equivalent to looking back in time to the first few 100 million years after the tremendous clap that started it all. The cosmos was simpler than its evolution, easier to compare against predictions. Astronomers first tried to see the earliest structures of the universe using the Hubble telescope in 1995. Over 10 days, Hubble captured 342 exposures of an empty look patch of space in the Big Dipper. Astronomers were astonished by the abundance hiding in the inky dark. Hubble could see thousands of galaxies at different distances and stages of development, stretching back to much earlier times than anyone predicted. Hubble would go on to find some exceedingly distant galaxies. In 2016, astronomers found its most distant one, called GNZ11, a faint smudge that they dated to about 400 million years after the Big Bang. This was surprisingly early for a galaxy, but it did not cast out on the lambda CDM model, in part because the galaxy is tiny with just 1% of the Milky Way's mass, and in part because it stood alone. Astronomers needed a more powerful telescope to see whether GNZ11 was an oddball or part of a larger population of puzzling early galaxies, which could help determine whether we are missing a crucial piece of the lambda CDM recipe. That's why the James Webb Space Telescope, or JWST, was born. Renowned as the largest, most powerful observatory ever launched from Earth, the JWST was built to revolutionize our understanding of the universe. Stationed 1.5 million kilometers away from Earth interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope carries a giant segmented mirror and exquisitely sensitive instruments that were designed to uncover details of cosmic dawn never before observed, and that promise was kept as the first discoveries were obtained within just weeks after JWST full operations were beyond astronomers' wildest dreams. It has seen galaxies breathtakingly close to the dawn of time, probed the atmospheres of exoplanets in unprecedented detail, and provided stunning new views of worlds in our solar system, but it's just getting started as Webb's vision reaches back into the first few 100 million years after the Big Bang, allowing it to obtain more and better data about newborn galaxies than any other facility yet built. At stake is nothing less than our very understanding of how the orderly universe we know emerged from primordial chaos. Webb's early revelations could rewrite the opening chapters of cosmic history, which concern not only distant epochs and faraway galaxies but also our own existence here in the familiar Milky Way. As JWST scientist Mark McCaffrey, a senior advisor for space and exploration at the European Space Agency, said, "You build these machines not to confirm the paradigm but to break it. You just don't know how they will break." Researchers use a version of the Doppler effect to gauge the distances of objects. This is similar to figuring out the location of an ambulance based on a siren. The siren sounds higher in pitch as it approaches and then lower as it recedes. The farther away a galaxy is, the faster it moves away from us, and so it's like stretches to longer wavelengths. And the magnitude of this redshift is expressed as z, where a given value of z tells you how long an object's light must have traveled to reach us. One of the first papers on JWST data came from NAU, the MIT astronomer, and his colleagues, whose search algorithm flagged a galaxy that seemed inexplicably bright and unaccountably distant. NAU dubbed at glass Z13, indicating its apparent distance at a redshift of 13. Further away than anything seen before. The galaxy redshift was later revised down to 12.4, and it was renamed Glass Z12. Other astronomers working on various sets of JWST observations were reporting redshift values from 11 to 20, including one galaxy called CHIR 1749 or CR2Z17 to 1, whose light appears to have left it 13.7 billion years ago, just 220 million years after the Big Bang, barely an eye blink after the beginning of cosmic time itself. These putative detections suggested that the neat store known as lambda CDM might be incomplete somehow. Galaxies grew huge right away in the early universe. You don't expect to see massive galaxies. They haven't had time to form that many stars, and they hadn't merged together, said Chris Lovell in a study published in November. Researchers analyzed computer simulations of universes governed by the lambda CDM model and found that JWST early bright galaxies were in order of magnitude heavier than the ones that formed concurrently in the simulations. Some astronomers and media outlet claim that JWST was breaking cosmology, but not everyone was convinced. One problem is that lambda CDM's predictions aren't always clear-cut. While dark matter and dark energy are simple, visible matter has complex interactions and behaviors, and nobody knows exactly what went down in the first years after the Big Bang. Those frenetic early times must be approximated in computer simulations. The other problem is that it's hard to tell exactly how far away galaxies actually are. In the months since the first papers, the ages of some of the alleged high redshift galaxies have been reconsidered. Some were demoted to later stages of cosmic evolution because of the updated telescope calibrations. CHIR 1749, for example, is found in a region of the sky containing a cluster of galaxies whose light was emitted 12.4 billion years ago, and Naidu says it's possible the galaxy is actually part of this cluster, a nearer interloper that might be filled with dust that makes it appear more red-shifted than it actually is. According to Naidu, CHIR 1749 is weird. No matter how far away it is, it would be a new type of galaxy that we did not know of, a very low-mass tiny galaxy that has somehow built up a lot of dust in it, which is something we traditionally do not expect. He said there might just be these new types of objects that are confounding our researchers. For the very distant galaxies, everyone knew that the most definitive distance estimates would require JWST most powerful capability. JWST not only observes starlight through photometry or measuring brightness, but also through spectroscopy or measuring a light's wavelengths. If a photometric observation is like a picture of a face in a crowd, then a spectroscopic observation is like a DNA test that can tell an individual's family history. Naidu and others who found large early galaxies measured redshift using brightness-derived measurements, essentially looking at faces in the crowd using a really good camera. That method is far from airtight. At a January meeting of the American Astronomical Society, astronomers quipped that maybe half of the early galaxies observed with photometry alone will turn out to actually be measured. But in early December, cosmologists announced that they had combined both methods for 4 galaxies. The JWST Advanced Deep Extragalactic Survey, or JADES team, searched for galaxies whose infrared light spectrum abruptly cuts off at a critical wavelength known as the Lyman break. This break occurs because hydrogen floating in the space between galaxies absorbs light because of the continuing expansion of the universe, the ever-rising raisin loaf, the light of distant Galaxies is shifted so the wavelength at that abrupt break shifts too. When a galaxy's light appears to drop off at longer wavelengths, it is more distant JADE's identified spectra with red shifts up to 13.2, meaning the galaxy's light was emitted 13.2 billion years ago. As soon as the data was down, JADE's researchers began freaking out in a shared Slack group, according to Kevin Hain, an astronomer at the University of Arizona. He said it was like, oh my god, we did it, we did it, we did it. He said these spectra are just the beginning of what I think is going to be astronomy-changing science. He said Brant Robertson, JADE's astronomer at the University of California, Santa Cruz, says the findings show that the early universe changed rapidly in its first billion years, with the galaxies evolving 10 times quicker than they do today. It's similar to how a hummingbird is a small creature, he said, but its heart beats so quickly that it's living kind of a different life than other creatures. The heartbeat of these galaxies is happening on a much more rapid timescale than something the size of the Milky Way, but were their hearts beating too fast for lambda CDM to explain? Astronomers in the public gaped at jwst. Images researchers started working behind the scenes to determine whether the galaxies blinking in our view really depend upon lambda CDM or just help nail down the numbers we should plug into its equations. One important yet poorly understood number concerns the masses of the earliest galaxies. Cosmologists try to determine their masses in order to tell whether they match lambda CDM's predicted TIM length of galaxy growth. A galaxy's mass is derived from its brightness, but Megan Donahue, an astrophysicist at Michigan State University, says that at best the relationship between mass and brightness is an educated guess based on assumptions gleaned from known stars and well-studied galaxies. One key assumption is that stars always form within a certain statistical range of masses called the initial mass function, or IMF. This IMF parameter is crucial for gleaning a galaxy's mass from measurements of its brightness, because hot blue heavy stars produce more light while the majority of a galaxy's mass is typically locked up in cool red small stars. But it's possible that the IMF was different in the early universe. If so, jwst, early galaxies might not be as heavy as their brightness suggests. They might be bright but light.